Welcome to the first lecture of this week. In the last lecture, we have seen the index theorem, and before that, we have seen the Bendixson's theorem. So these were all sufficient conditions for the non-existence of periodic trajectories. In this lecture, we are going to see a sufficient condition for the existence of periodic trajectories, and that is going to be called Poincare-Bendixson's theorem. So let us start with that topic. Bendixson theorem. Let us write an S here. So I will directly go into the statement of the theorem. So let us write this. In this case, this is going to be a sufficient condition for the existence of periodic trajectories or limit cycles. Periodic trajectory of a periodic trajectory and a limit cycle or a limit cycle. Okay? So the statement of the theorem is as follows. If a trajectory of the second order system x dot is equal to f of x remains in a finite region, R, in the phase plane, then one of the following is true. A, there are three conditions here, and the theorem says that if a trajectory of a second order nonlinear system remains in a finite region, a bounded region, then one of these three possibilities should be correct or true. Trajectory goes to an equilibrium point. B, trajectory goes to a stable periodic trajectory or limit cycle, or limit cycle. And the third possibility is that the trajectory itself is a periodic trajectory. Or limit cycle. Okay? So this is Poincare-Bendixson's theorem. So there are some things to emphasize in this theorem. Well, the first thing is that the theorem says that the second order system. So we assume that X has two elements, and X1 and X2, and therefore our state space is R2. And this is important because as soon as we go to the third order systems, Poincare-Bendixson's theorem start not to hold. Okay? So in third order systems, you can find third order systems which would have bounded trajectories constrained to a finite region, but none of these three possibilities are correct. And actually, starting from the third order, we start to see some phenomenon called chaos, and chaos actually it means that none of this is happening. Something strange starts to happen in the dynamic behavior of the system. And actually there are third order systems
whose trajectories remain in a bounded region, and the trajectory does not, those trajectories might not go to, do not go to an equilibrium point. They do not go to a stable periodic trajectory, and they are not periodic trajectories. So the trajectory of the system remains in a three-dimensional cube, for example, and it wanders around forever. It never converges, and it never goes to a stable oscillation of some form. So every point that it arrives becomes a new point, and it never passes a point that it has passed before. Okay? Such type of systems are called somehow strange attractors, and a very famous example is named after the meteorologist Lorentz, and it's called Lorentz attractor. And actually it marks the beginning of the so-called chaos theory in nonlinear system or nonlinear dynamical systems. So here, but this is for the second order systems, nothing strange can happen, and that is what Poincare-Bendixson's theorem is claiming. So if we have a second order system, and if a trajectory of that second order system remains in a bounded region, then one of these three possibilities should be correct. So I have my state space, and in this state space, I have a bounded region R. Okay? So this is x1, x2. And what can actually happen? And I know that in the assumptions of the theorem, we are said that a trajectory of the system remains in this finite region. So there is a trajectory of the nonlinear system x that is equal to fx, and we know that forever it remains in this region. Okay? And then what are these three possibilities? The first possibility is that there is an equilibrium point here, and then that trajectory it might wander around in this region, but it is at the end converging to that equilibrium point. Okay? So that is the first possibility. And the second possibility is that the trajectory is not a periodic trajectory, but it converges to a periodic trajectory. So I have here, the region is again like this. So we have a trajectory which is not a periodic trajectory, but it converges to a periodic trajectory. Okay? So I have a periodic trajectory here, and my original trajectory starts from here, and then it goes to a stable periodic trajectory, and it oscillates forever there on that periodic trajectory. Okay? And the third condition is nothing but what happens when I erase this part. Okay? The third condition is that the trajectory itself is a periodic trajectory. Okay? So if I start the trajectory somewhere here on this periodic trajectory, then I would get just this single periodic trajectory when I start the system here, and the trajectory never goes outside. Okay? So these are these three possibilities. As I told you, as soon as we go into third order systems, we start to get, so our state space would become a three-dimensional space, and suppose that we define a cube or a rectangular region like this, then the system trajectory might remain here in a region, and it might not go to an equilibrium point. It might not go to a periodic trajectory, and it might not be itself a periodic trajectory. So it might actually wander around in this finite region. It might wander around in this finite region without actually crossing a point it passes more than once. Okay? So it would always remain here in this region, and it might not pass a point that it passes more than once, and it might still remain in a bounded region. Okay?
So those systems are really interesting, and the name given to those systems are really giving that taste. And the name given to those three-dimensional or larger dimensional systems are attractors or strange attractors, whose theory is going to be beyond the scope of this course. Okay. So here I told you that this theorem is actually a sufficient condition for the existence of a periodic trajectory or a limit cycle. But here we see something. So we see that there are three possibilities here, and only two of them would involve a periodic trajectory. Okay? So how can I therefore use this theorem to obtain a sufficient condition for the existence of a periodic trajectory? Okay? Or how can I change this theorem a little bit so that I can predict the existence of a periodic trajectory or a limit cycle? And that is going to be made using a corollary. So how can we do that? If we eliminate the first possibility, then the last two possibilities would always involve a periodic trajectory or a limit cycle. Okay? If we eliminate the first possibility, for example, if we say that in this finite region, if there is no equilibrium point in that region, then the first possibility would become impossible. And then the last two possibilities should be true. So that means the existence of a periodic trajectory or a limit cycle. So let us say that. So if a trajectory of the system x dot is equal to f of x, this should be still a second order system. X dot is equal to f of x remains in a finite region in which no equilibrium points exist, then we know that the first possibility, the first condition or first option is not possible. That means that either the trajectory should go to a stable periodic trajectory, or it should be itself a periodic trajectory, meaning that in that region there must be a periodic trajectory. Okay? Then there exists a periodic trajectory or limit cycle in R. Okay? So this is what, therefore, the sufficient condition that we can give using the Poincare-Bendixson's theorem for the existence of a periodic trajectory or a limit cycle. All right? So now we are going to be using this theorem to actually show that some system, in an example, some system should have a periodic trajectory or a limit cycle. But before that, I need to talk about something. Remember that in the previous lecture, we have seen the so-called index theorem. Okay? And in this index theorem, we gave a corollary to that theorem, saying that all periodic trajectories of the nonlinear system x dot is equal to f of x should contain at least a node, a focus, or a center. Okay? So we said that for each periodic trajectory there should be at least one equilibrium point inside, encircled by that periodic trajectory. Okay? But does this not contradict that fact? So we are saying that if a trajectory of the system x dot is equal to f of x remains in a finite region in which no equilibrium point exists, then there exists a periodic trajectory in that region R. So as soon as I assume that there is no equilibrium point in that region R, this possibility is not possible. So this option is not possible, and these two options should be correct. Okay. But I know by the index theorem there should be some equilibrium points here and here. Okay. So how can this corollary be correct when we think about the index theorem as well? Because when I look at these two cases, I definitely see the periodic trajectories, but they should come with their own equilibrium points. There might be more than one actually. Okay, but there should be at least one node, center, or focus encircled by these periodic trajectories. So how can this corollary be actually correct? Okay, that is my question. So do we have a contradiction here in the theory? You might guess that. Of course there is not. So let me try to explain. So in general, when we look at the Poincare-Bendixson's theorem, these pictures that I have drawn are somehow misleading. Okay? So here, the regions R that I have shown here, they were all simply connected domains somehow, or simply connected closed sets here. Okay? So these regions that I have drawn here, they are somehow misleading. Actually, for the Poincare-Bendixson's theorem and for the index theorem to be correct at the same time, we can say that these regions cannot be in this form. Okay? So these regions are going to be usually in the following form. They are going to have some holes in them. So this is, okay? So this is going to be our R. Okay, so the finite regions that are going to be valid for the corollary of the Poincare-Bendixson's theorem are going to be like disks in the state space. Okay, so then we are going to say that there is going to be a trajectory of the system here. Okay. The periodic trajectory of the system is going to be here in this finite region. Okay, this shaded region is my R, and the equilibrium point is going to be somewhere here. Okay, so you see that in this shaded region R, there is no equilibrium point. Okay, and the region R is a finite and bounded region. Okay. So when the corollary, so the regions R that would be valid for the corollary of the Poincare-Bendixson's theorem will always come in this form. Okay? I see that the region R is bounded or finite, okay? And it doesn't contain an equilibrium point, as you see, because it has a hole in it. There is no condition in the Poincare-Bendixson's theorem that this region R, finite region R, should be a simply connected region. Okay? It can always have, and for the corollary, it always has holes in it for the equilibrium points to live. All right? So then if a trajectory of the nonlinear system, if it never leaves this disk here, and in that case we know that there is no equilibrium point in that disk, then there should be a periodic trajectory in that disk by the corollary of the Poincare-Bendixson's theorem. But we see that this periodic trajectory still encircles, it should still encircle an equilibrium point. And this equilibrium point is still outside this region R. Okay, so there is definitely no contradiction here, and actually that we are going to see that in the example. So in the example we solve, the region that we are going to be dealing with is going to be a perfect circular disk. Example. Consider the following system. X1 dot is equal to x2 plus x1, 1 minus x1 square minus x2 square, and x2 dot is equal to minus x1 plus x2, 1 minus x1 square minus x2 square. At the beginning of the concept of limit cycles, we have actually dealt with this example, and we showed that this example had a limit cycle. Okay. So how the task here is that show that there exists a periodic trajectory or a limit cycle of this system in the region defined as, so I define R as follows. It is the points x1 and x2 such that x1 square plus x2 square smaller than or equal to 1.5 and 0.5. Okay? So we need to show that there exists a periodic trajectory or limit cycle of this system in the region defined as this. So what is this region? Let us look at this region. I have x1, x2, and we know that these are denoting some circles. So I would have the smaller circle here like this with the radius square root 0.5. Okay, that is this radius, and the second circle is going to be like this, and in this case this is square root 1.5. Okay? And this is square root 0.5, square root 1.5. So that is my region. So you see that it has a hole in it. It's not a simply connected region here. It has a hole in it. But in the Poincare-Bendixson's theorem, there is no such condition. So the theorem is still applicable to this region. Okay? So here what I need to do is that to show that if I start a trajectory of this system inside this region, then that trajectory is never going to leave this region. Okay? If I start the system whose equations are given like that, if I start the system initial condition somewhere inside this region, the system trajectory is never going to be able to leave this region. So it's going to remain forever in that region R. So this is our region R, and to show that there exists a periodic trajectory or a limit cycle of the system inside this region, I need to show that the conditions of the Poincare-Bendixson's theorem would hold for any trajectory started in that region. All right? That is the first condition of Poincare-Bendixson's theorem. So I need to have a trajectory that doesn't leave this region. The second condition is coming from the corollary here. And there shouldn't be any equilibrium point in that region. That is actually relatively easier to show. Calculate the equilibrium points of this system, and then you're going to see that the only equilibrium point is going to be the origin.
Okay? Try to calculate the equilibrium points of this system and show that xc equals to 0, 0 is the only equilibrium point of this system. Okay? Meaning that there is an equilibrium point indeed here. Okay? So when we have a periodic trajectory, we are not going to violate the index theorem here. Okay? The result is going to be, so what can be the type of this equilibrium point? Can it be a saddle point? So if I can show that there exists a periodic trajectory of the system here, then I know that n equals to s plus 1 by the index theorem. So that equilibrium point should be either a node, or it can be a center, or it can be a focus. Okay? But it cannot be a saddle point. All right? So then we definitely satisfy the condition of the corollary, the second condition. No equilibrium point exists in that region R. Okay? Then what we have to show is that in order to be able to make the Poincare-Bendixson theorem and its corollary applicable, we need to show that a trajectory of the system remains in that region when it starts in that region. Okay? Actually, it really, so here let us try to show that. In order to be able to show something like that, we are going to be using a simple idea that we are going to also use in the rest of this course quite a lot. Okay? And that idea is going to involve an auxiliary function, v of x. So here let me define that auxiliary function. V of x, I will define it here like this, x1 square plus x2 square. Okay? So how does this function look like? So here I show v of x, and I have x1 here, and I have x2. This function is a ball-like function, like this, and its level curves would be just circles, like this. Okay? And this is my state space. This is where our states would live. So a trajectory of the system would be living in this x1, x2 plane, and the idea that we're going to use is going to involve how the value of v of x would change on a trajectory of this system. Okay? On a trajectory of this system, at each point I can actually evaluate the value of this v. All right? And I can actually look at those values, whether those values are increasing or decreasing or remaining constant. Okay? Then what can I conclude? So suppose that this function, I know that this function has level curves like circles here. For example, on this one, v of x is equal to 1. On this one, I have v of x is equal to 2, etc. Okay? So v of x is increasing as I get away from the origin, and v of x is getting smaller and smaller as we approach origin. Okay? And you see that here, these level curves are similar to the boundaries of our region here. Okay? So here, on this outer boundary, I have v of x is equal to 1.5, and on the inner boundary, I have v of x is equal to 0.5. Okay? So now suppose that
a trajectory of the system is exactly on this outer boundary. Okay? Suppose that a trajectory of the system is exactly on this outer boundary of this region R. Okay? So suppose that the trajectory is exactly here. At this point, if v of x decreases, I know that this trajectory is going to go towards inside this region. Okay? At this point, if v of x decreases in time, then that means that the trajectory is going to go towards inside this region. On the other hand, if v of x increases, I know that the trajectory is going to go towards outside. Because that is the only way that v of x can increase. V of x increases as we get away towards outside these circles, and v of x decreases in time as we go towards the origin. Okay? So if I find, so it is all related to what v dot of x is. V dot of x is d over dt v of x. Okay? So if I can look at the rate of change of v of x in time, then I can actually, that v dot, the sign of v dot, would tell me how the trajectory of the system would behave on these boundaries, whatever x I use here. Okay? Similarly, I can actually check v dot of x on this boundary, and I can try to understand if the trajectory started here would go towards inside or would go towards the outside of the circle, or they would go towards inside the region R, or they would go towards outside the region R. Okay? So then what can this type of reasoning would give us? So suppose that I have a trajectory of this nonlinear system. Okay? So, and suppose that I would like to show that this trajectory can never get outside this region. Okay? I have a trajectory here, and I would like to show that this trajectory cannot go outside this region. So suppose that we have the reverse situation. Suppose that we want this trajectory to get outside this region. Okay? In that case, this trajectory definitely cannot jump from here to here. It needs to go continuously towards outside. Okay? So if a trajectory gets outside this region from the outer boundary, it has to cross this outer boundary. Okay? And since it is crossing the outer boundary and it is going outside, v dot of x should be positive there. Okay? Because otherwise it would either stay on this outer boundary, or it would go inside. Okay? So if a trajectory is going outside of this region, by crossing the outer boundary, v dot of x should be positive. Okay? Otherwise it cannot go. At this point, v dot of x should be positive. Okay? Similarly, if the trajectory is going outside this region, by crossing the outer boundary, v dot of x here at this point should be negative. Okay? Why? Because for a trajectory to go inside, the v should decrease on that trajectory. Okay? So therefore, if a trajectory is going outside this region, by crossing the inner boundary, then at its crossing point, v dot should be negative. Okay? Because otherwise it cannot go towards inside. All right? So here, therefore, in order to be able to show that a trajectory starting from inside this region never leaves this region, it is sufficient that I show that v dot of x on all of these outer boundaries, v dot of x is actually negative or 0. Okay? And in the inner boundaries, if I want to show that no trajectory started inside can go outside, I need to show that v dot of x is 0 or positive. Okay? So in order to be able to show that no trajectory goes outside like this, I need to show that on all points on this outer boundary, v dot of x is either 0 or negative. Okay? So no trajectory can get outside like this. Okay? And in order to be able to show that no trajectory goes outside this region by crossing the inner boundary, I need to just show that v dot of x on that inner boundary is always positive or 0. Okay? If I show that, then I know that v dot of x at that point can never be negative, so this trajectory can never get inside by crossing that inner boundary. Okay? So then how can I calculate this v dot of x? It is really nothing fancy, it's just a chain rule. Is equal to, by definition, d over dt v of x. V itself is only dependent on x, and it is dependent on time only through these x values, x1 and x2. Okay? So here, this total derivative is going to be del v over del x1 over del t, plus del v over del x2 over del t. A chain rule. Okay? But this del x1 over del t is x1 dot, and this is x2 dot. All right, so we have del v over del x1 dot, plus del v over del x2 times x2 dot. This is what v dot of x is. We are going to be interested in this derivative. And we know that, and this is nothing but the rate of change of v on the trajectories of this system. Okay? If this thing is positive, then that means that on the trajectory of this system, this v is increasing. So we are going towards outside. We are going towards outside on that ball. All right. Similarly, if v dot is negative, then that means that on this trajectory, the v dot is decreasing, meaning we are going towards inside this region, towards the equilibrium point. If v dot is equal to 0 on the trajectory, what does that mean? If v dot is equal to 0, then that means that our trajectory is traversing one of these level curves. Okay? If v dot is 0, then that means that v is not changing, meaning that our x1 and x2 would be traversing these level curves. Okay? It remains on one of these circles if v dot is equal to 0. Okay? So now let us try to calculate this v dot of x using our system equations. V dot of x is equal to del v over del x1, take that partial derivative, 2x1, times x1 dot. x1 dot is coming from our system equations. x2 plus x1, 1 minus x1 square minus x2 square here, plus del v over del x2, it is 2x2, and I would have x2 dot minus x1 plus x2, 1 minus x1 square minus x2 square. So I see that these x1, x2 values, they are cancelling, and I would have here I would have x1 square plus x2 square times 1 minus x1 square minus x2 square. Okay? That is v dot of x. All right? This is the rate of change of the function v on the trajectory of the system. Okay? Depending on whether this is positive, negative, or zero, I can extract information about where the trajectories are going towards. Okay? If v dot is negative, we are going towards inside, towards the equilibrium point. If v dot is positive, we are going towards outside. We are getting away from the equilibrium point. If v dot is equal to zero, we are on these level curves. Since v is remaining constant in time. Okay? So now let us look at the outer boundary. Outer boundary of R. In the outer boundary of R, I know that x1 square plus x2 square is equal to 1.5. All right? So it is good that this function v dot depends on x1 and x2 only through x1 square plus x2 square. Okay? So I can substitute this value to calculate v dot of x on the outer boundary. V dot of x on the outer boundary would be, let me erase this because I don't know the exact value of x. V dot on the outer boundary is going to be 2 times 1.5 and 1 minus 1.5. Okay? We are only interested in the sign of this number. So we see that this is strictly smaller than 0. Meaning, if a trajectory of the system reaches this boundary, it has to always go towards inside. Okay? So on the boundary, all trajectories are going towards inside this region R, because v dot is getting smaller. So we need to go inside the circles towards the equilibrium point. So we know that in the outer boundary, all trajectories should go towards inside this region. So what does that mean? That means that no trajectory started inside this region can cross this outer boundary and go outside. Okay? These trajectories should be always continuous. Okay? So they cannot really jump. So there is no teleporting like that for these systems. So these trajectories should always go from one point to the other point by crossing continuously at each point in between. All right? So here we understand that no trajectory started inside this region can leave this region by crossing the outer boundary. Because if it crosses the outer boundary, it needs to go back inside. Okay? It cannot go outside. We have shown that on this outer boundary, all trajectories should move towards inside. That means that no trajectory can get outside this region by crossing the outer boundary. Okay? That means that no trajectory can go outside the region R by crossing the outer boundary. Okay? That is our conclusion from this. And now let us investigate the inner boundary. Inner boundary of R. And in this case, we know that the inner boundary, x1 square plus x2 square, is equal to 0.5. All right? Now let me substitute it in v dot. V dot is equal to 2 times 0.5 times 1 minus 0.5. Okay? We see that this number is positive. So at every point on the inner boundary, v dot is positive, meaning that v is going to increase at each point on this boundary. That means that if a trajectory of the system is here, it needs to move towards inside this region R. that actually means that no trajectory of the system started inside this region can go outside this region by crossing the inner boundary. Okay? Because in order for it to be able to cross and pass the inner boundary, this v dot should be actually negative there. All right? So let me write that result also. Where? Here. No trajectory inside R, of course, can go outside R by crossing the inner boundary. Okay? So then what does this mean? This means that if I start a trajectory inside this region R, that trajectory cannot go outside like this, cannot go outside like this. That means that it has to remain in this region forever. Okay? It may never leave that region. So that means that a trajectory started in R can never leave R, can never go outside R. Okay? That means that any trajectory started in this region will remain in R forever. And there is no equilibrium point in R, meaning that the corollary of the Poincare-Bendixson theorem would hold, and that means that in R there should exist a periodic trajectory. Okay? So we need to have a periodic trajectory here, like this. And actually, in the earlier lectures of this course, we have actually passed this system into polar coordinates, and we have seen that in polar coordinates this system looks like r dot is equal to r1 minus r square, and theta dot is equal to -1. We have seen that the equations of this system are given like this. So at r equals to 1, we have a limit cycle. And we are going to have a stable limit cycle there by the Poincare-Bendixson theorem. Okay, so this actually completes the investigation of Poincare-Bendixson's theorem. So we have, with this topic, we have finished the topic of the investigation or the results on the existence and non-existence of periodic trajectories. And from this point on, we are going to start seeing some approximate methods to predict the existence of periodic trajectories, and we are also going to, with that method, we are also going to be able to estimate the frequency and the amplitude of the oscillations that are observed in a nonlinear system. That method is going to be called describing function analysis, and we are going to see that it is an approximate method, but it is going to be quite powerful in predicting the parameters and the existence or non-existence of the periodic trajectories. With those approximate methods, we don't have any guarantees. The index theorem can say that there exists no periodic trajectories, certainly. This Poincare-Bendixson theorem can say that there exist periodic trajectories, certainly. But with the describing function analysis, because we are going to have approximations in the nonlinear system, we are actually, the results that we obtain will not be certain. They would always be approximate results, and they might not be holding in reality. But nevertheless, it's a nice engineering approach that we can apply to nonlinear systems, and we're going to see that it's a form of linearization. But in this case, the linearization will not be in frequency domain, is not going to be in time domain as we did before, but it's going to be in frequency domain. Okay? But that is the topic of the next lecture. That's all for this one. Thank you very much for watching.